Okay, so when we left off, this is where we were. We had just learned what comb filtering is, and we had spent a little bit of time listening to it, so you understand a little bit of what it is and what it sounds like. And I ended the session saying, like, you have never heard a sound in your life that wasn't comb filtered. And that is true. I stand behind that statement because unless you have stood inside of a truly anechoic room, which I suspect very few of you, if any, have, every sound that you have heard has arrived at your ears at least twice. Once directly from whatever made the sound, and the second time it would have reflected at least once off of some surface before it found a way back to your ears again. And so that is the most common source of comb filtering, is when sound reflects off of some surface, because that's what it does. We'll learn more about that later. But sound can reflect off of walls and tables and stuff like that. It can reflect off of people even. And then find its way across the room to you. And when it does that, you hear it twice, but at a different time. And therefore, it does interact somewhat destructively. But there's an important thing to understand about comb filtering. The really, really bad comb filtering, which is the kind that we heard last time, is comb filtering that happens when these two sounds are basically equal in every way other than time. So they are different in time, but otherwise identical. Identical in amplitude, identical in their frequency components, so on and so forth. They have to be perfectly identical. If any of those values change between them, like the most common one is amplitude. If there's a amplitude difference between them, they will not comb filter perfectly. I mean, those cancellations will not be perfect. And so in the case of reflections, for example, usually that reflected energy took a little bit longer to get to you, and therefore it'll be a little bit quieter for reasons that we'll learn later. And therefore, the comb filtering will not be quite so severe because they will not be perfectly identical in level. And so that's the first reason why you're able to walk around on this planet hearing comb-filtered sound all the time and not completely lose your mind. It's because the comb filtering is not perfect, okay? You're not hearing perfect cancellations and reinforcements most of the time because there's usually not a perfect match of level between the two sounds that you're hearing, or the many sounds you're hearing. There's another reason why you don't notice it as much, and it has to do with why the last example that we played, which was when I comb filtered it in the air, and then I played music, and you had to pay really close attention to really hear that comb filtering when I did it that way. And that's because it mimics what you hear all the time. And so our ear-brain system has learned how to cope with this really well. This notion of hearing the sound more than once in the air. We've had to learn to cope with that, otherwise it would just be impossible to listen to anything. And so we have developed some blind spots, essentially, in our ear-brain system. And when those cancellations and reinforcements get really close together, then our ear-brain system does not have the resolution to tell those things apart. So when you've got cancellations that are happening close enough together, and on average, this window is about a third of an octave. It's called the critical bandwidth. It's a moving target a little bit as far as like how wide that is, but generally it's about a third of an octave. And if you've got a whole bunch of cancellations and reinforcements happening within a third of an octave, your ear-brain system kind of ignores it. In the same way that your eye-brain system ignores multiple still shots thrown at you 24 times a second and does not interpret those as individual pictures. That's what movies are, right? Films are still shots that are just thrown at you really fast. and you don't perceive them that way. You perceive them as a continuous image. It's a similar thing with comb filtering. If those cancellations reinforcements are happening within that critical band, you sort of ignore it and you pretend as though it's not there. And you sort of interpret what the frequency response probably should be, and that's what you hear, okay? So that's how we've learned to cope. Okay? We can use that to our advantage a little bit, because sometimes, well, you can't completely eliminate comb filtering. It's just not possible. So your goal then is to eliminate the kind of comb filtering that your ear-brain system can't ignore, right? The stuff that your ear-brain system is going to notice, that's the stuff you want to get rid of. And you don't need to worry about the stuff that your ear-brain system cannot or will not acknowledge because it's not bothering you. And so one of the ways that we can do that is we can push the comb filtering into those critical bands, okay? And as you'll see in the math that we're about to do, you can predict this comb filtering and how it's going to happen mathematically. And the longer the delay, the longer the time between the two sounds, the lower in the spectrum that first cancellation happens. So right here, you know, this first cancellation, the longer period of time there is between the two sounds, that first cancellation moves down lower on the frequency spectrum. And when that happens, all these other ones move as well. And as you can see, as you go up, they get closer and closer together. So if you can take this whole thing and you can shift it down farther, lower in the frequency spectrum, then you can create comb filtering that is, you can push that dense comb filtering all the way down into the full audible spectrum, and your brain system is able to quite happily ignore that. And this is something that you can and ought to do in your day-to-day life as a sound designer. Manipulating this comb filtering. You can't make it go away, but you can shift it into the critical bandwidth so that the ear-brain system doesn't notice it. Okay, and we will kick around some scenarios of how that might work. But you will absolutely, I mean, good sound designers and sound engineers are doing this. They are keeping an eye on this thing, and they are manipulating time to their advantage. Okay, any questions about that? All right. Well, let's start doing some math about it then. So, first question is, what delay applied to one of two 250 hertz sine waves would make it 90 degrees out of phase with the other? All right. Well, let's start by just sort of drawing a little graph of a sine wave really quick here. Okay? And we will call this 250 hertz. 250 hertz has a certain wavelength, doesn't it? And what would that wavelength be? That would be 1,000 divided by 250, which is what? 4 feet, which means that this distance here is 4 feet, isn't it? For this scenario. Okay. Well, 90 degrees out of phase would be what part of this wave would we label as 90 degrees phase? Yeah, it would be right here. That's 90 degrees, right? Okay. Well, what portion of this wave is that? If we were to label that as like a fraction or a decimal value or something.
1/4.
Yeah, 1/4, right? Because like here, this would be a half, right? So yeah, this would be 1/4. Okay, so what's a fourth of 4 feet? 1 foot. Okay. So I don't know what the delay is, but I know that whatever that delay is, it could be represented by a 1 foot offset, right? So what is 1 feet converted into time? When we're doing our head, it's 1 millisecond. Because it's foot per millisecond-ish, right? 1,000 feet per second is the speed of sound. 1,000 milliseconds in a second. 1,000 divided by 1,000 is 1 foot per millisecond. So yeah, it's 1 millisecond-ish. You delay two 250 hertz sine waves. One of them gets delayed a millisecond, and they will be 90 degrees out of phase. Okay? Everybody okay with that? It's actually a pretty easy question. I just did it the hard way, but I did it very, very slowly with lots of steps. But really, there's not a whole lot to that. Let's prove it. Okay, here's the same question, but just with a different value. Okay, so we know that, so same question, but what would make it 270 degrees? Okay, well, we already know that we're talking about a 4-foot wavelength, right? Well, let's mark it down. So 0 degrees would be 0 feet. Okay. 360 degrees would be 4 feet, right? 180 degrees would be 2 feet, which means 90 degrees would be 1 foot. And 270 it is 3 feet, right? So again, looking at my wave, this is 0 feet. This is 4 feet. This is 2 feet, 1 foot, 3 feet, right? This is also known as 0 degrees. This is known as 360 degrees, 180. Oops. This is 90 degrees. This is 270 degrees. Yeah? So we're talking about this 3-foot thing, right? So 3 feet equals 3 milliseconds. That is the answer. Okay? Not too bad. We did a lot of math there we didn't have to do to get this answer, but just I'm trying to drive the concept home here. Okay? Everybody ready for the next one? Yeah. All right. All right, so let's talk about how we do this with a calculator. So I've got this little equation that that my friend Jennifer Berg came up with. She's the one that I wrote my book with together. And I was like, Jennifer, I need a really easy way to calculate comb filtering. There's lots of ways to calculate this. And it's like, well, I need an easy way to do it. And she said, okay, well, let's figure that out. So this is what she came up with. And I think it's actually not too bad. So
I would say that one thing I would caution is putting I in there, because some people might mistake that for the imaginary number.
yeah, it's not. So I will talk about what I means. But basically, we need to define some of these variables, okay, in this equation. So this top equation, this is how you find out which frequencies get canceled out, okay? And T equals the delay, okay? Delay, this is in seconds, not milliseconds, okay? So T equals the delay difference between the two sounds in seconds, okay? And then I equals, there's a pattern of cancellations here, right? There's multiple frequencies that get canceled out when comb filtering happens. So I is the index label of the cancellations starting at 0, okay? So I is the frequency. Index, okay? 0 based. In other words, the first cancellation that would happen, we would call that 0 cancellation is going to be frequency I. The next cancellation would be, well, frequency 0, frequency 1. Third cancellation would be frequency 2, so on and so forth. So I'll explain. And then to figure out the reinforcements, you use this equation. And I just, another way of thinking about I is it's just all integers greater or equal to 0. This goes on forever. So you just keep plugging in one integer after another, starting at 0 for I, and you will get, every time you run that equation with a new value for I, you will get a new frequency. Okay? That's another way of thinking about it. So let me demonstrate how this works. Are you ready?
No.
Okay.
So many angry no's.
Frequency index?
That's what I think about it as, is the frequency index.
I want to know if that's what you
Yeah.
And that's a 0 base?
Yeah.
Okay.
In other words, starting at 0.
That has always been.
Yeah.
When you, so like, if you're looking for the second cancellation, your I is 2? Is that what that's
1.
saying?
I is 1.
Okay.
Oh, so the first cancellation is where I is.
Yeah.
Oh.
Yep. Sorry, I probably didn't write that very well. But when it was 0 base, that's what I mean. The first one starts at 0. So you start counting at 0, not at 1, which is how computers count. And you should probably get used to counting that way anyway, because you deal with computers a lot. I'm just using C to talk about cancellation. Don't worry about that. This will make sense when I start running this math, okay? So don't overthink it right now. It's about to make a lot more sense, okay? So
With the word problems, like just the last two we just did, I have always been terrible at word problems because it makes my brain angry.
well,
So like I can understand the math you're doing, but I can't piece together how that math fit, does that fit?
yeah, you're going to have to get good at that.
Okay. I thought you were gonna be like, yeah, there's this really simple trick.
Well, it's about understanding what you're doing.
Okay.
Okay? This is not about understanding a mathematical equation. This is about understanding what is happening. And if you understand what is happening, then the math is just a tool to express what's happening. Okay? This is, a lot of the math you've probably done in your life so far has been very abstract. Okay? It's just been numbers for numbers' sake. Right? You've just been doing math on numbers for no particular reason other than they're numbers, and you're supposed to know how to do things with numbers. Okay? We're now doing math that has a reason, right? That is connected to something real that actually matters to you. And so I think you'll find that if you can kind of like take that leap and be like, okay, it's not just numbers anymore. These numbers mean something. Okay? That's when this will start to make sense. So, here's the question. Connor, you got a question?
Oh, I think I've answered it myself, but just on the reinforcements, the first reinforcement is still I.
Yeah.
Okay.
Yep.
Okay, I just wanted to make sure there wasn't an offset.
Nope, there is not.
Two accounts.
Okay, so here's the thing. You got two equal signals, and they arrive at the listener 1.5 milliseconds apart from each other. In that scenario, that'll create a comb filter, because that's what happens when you combine two identical sounds out of time. It comb filters, we know that. So in that scenario, what would be the first 3 cancellations and the first 3 reinforcements? Well, okay, well, let's see if we can do this. So I'm going to just start a little table here, okay? And I'm going to use C for cancellations. And I need 3 of them. So I'm going to do, starting at 0, and I'll do 0C, 1C, 2C for cancellations. I'm looking for 3 cancellations here. Let's do those first. So for a cancellation, I'm going to do 2 times 0, 0 for I, right? Plus 1 divided by 2 times t. Now what is t in this scenario?
1.5 in seconds.
So the time I gave you was 1.5 milliseconds. We need to convert that to seconds. How do we do that?
Move it over 3 decimal points, but you have to divide by 1,000 in this case.
Exactly. So we got to divide by 1,000. So what is 1.5 divided by 1,000?
0.0015.
0.0015. Okay, did anybody else get that? Okay, keep up with us here. We're doing this one step at a time. The way to do this is you focus one step at a time. The step we are focusing on right now is turning 1.5 milliseconds into seconds, because that's how this math works. So 1.5 milliseconds equals how many seconds? 0.0015. And how do we know that? Because to go from milliseconds to seconds, you divide by 1,000. So 1.5 milliseconds divided by 1,000 gets you 0.0015. Okay, everybody with me? Yes. 0015. There you go. That's the thing. So it's, well, we could simplify this now. We know 2 times 0, right? That's 0, which means all I'm left with is 1. So I'm looking for 1 divided by 2 times 0.0015. Right? This just got a lot simpler. What is 2 times 0.0015?
0.003.
2 times 0 plus 1 is where I started, right? 2 times 0 is 0, right? I'm just going left to right here because I've got more room left to right than I have top to bottom. So I'm just getting rid of the stuff I don't need. 2 times 0 is 0, so I don't need 0. So I just got 1 divided by 2 times 0.0015. So what is 2 times 0.0015?
0.003.
Okay. Anybody else get that? Yes? Okay. So what is 1 divided by 0.003? 333.33 hertz. There you go. There's your first cancellation.
That was the first one. That's crazy. With my passing the paper towels, I need more towels. I'm so sorry.
Yeah.
I'm so sorry. I'm itchy in my nose.
Thank you.
Okay. Great. Let's do the other one now. I'll do this one in blue, okay? So this is going to be 2 times 1 plus 1 divided by 2 times 0.0015. Okay? Yeah, I don't need to do that other thing again. I've already done it. We already know it's 0.0015. Okay. Well, 2 times 1 plus 1. So what's 2 times 1? 2. Okay. So we're really talking about 2 plus 1 divided by what's, and we already know 2 times 0.0015 because we already did that, right? So that's 0.003. So all I'm looking at is 2 plus 1 divided by 0.003. Well, 2 plus 1 is 3, right? So 3 divided by 0.003. I mean, I'm doing this the long way, just to make sure I don't leave anybody in the dust here. Okay? Let's 3 divided by 0.003. 1,000 hertz. Yeah? I told you it'd make more sense once we started doing it. Okay?
I can never figure out math if you just explain it to me to see it happening. Right.
Okay. Let's do the other one now. So, oops. Come back. All right. So let's do this one. So this is going to be 2 times 2 plus 1 divided by 2 times 0.0015. Well, we can simplify this. 2 times 2 is 4, right? 4 plus 1 divided by 0.003. We know that. 4 plus 1 is 5, so 5 divided by 0.003. What is that?
1,666.67.
Okay, anybody else get that?
I did.
Okay, Reese got that. I need one more before it's right. Connor got that? Okay, it must be right. There you go. We got the first 3 cancellations. We did it.
We still need the reinforcement.
Right?
Jason did it.
Woo! We were there.
And we were
We were there while Jason
and
did
we're
it.
only halfway there.
We were learning.
That's
It's
crazy.
fine.
That's crazy. That's so much math.
Building to like for the reinforcement.
So
That
here's
equation.
there's the first 3 cancellations right there. That's the first half of the answer. Okay? Everybody all right?
How long would it take you to do this problem? Like
Not this long. But I've been doing this math for a long time. I'm not really good at math, but the math I know how to do, I do a lot of, and so I'm fast at it. But okay, let's try again now.
So to start the hold on.
So I'm going to go back. I'm just resetting my ink. Chill out.
So to start
Um,
the reinforcement.
I'm sort of out of space here, aren't I?
If I is the same thing that we started with the zeros, C1, C2, like that.
Well, now we're going to go after reinforcements. Okay. Yeah, so I'm going to call those R for reinforcements. So 0R, 1R, 2R. Okay, so this is going to be 0 plus 1 divided by time, which is 0.0015. We already figured that out, right?
So using that for everything, that's our base.
Yeah, that's it. You know, that's t. That's not going to change in this scenario. Okay, so, well, 0 plus 1 is 1, so we're really talking about 1 divided by 0.0015. What's that? 666.67. Maybe you're seeing a pattern emerge. Okay. Now let's do this one. So this is 1 plus, oops, hang on, let me do this in the other color. 1 plus 1 divided by 0.0015 equals 2 divided by 0.0015. What is that?
1,333.33.
Okay, anybody else get that? Connor got that? Anybody else? Okay, good. Must be right then. Okay, this one is going to be 2 plus 1 divided by 0.0015. That's going to give me 3 divided by 0.0015. Yeah? What's that?
2,000.
2,000 even? There you go. There's the other half of the answer. Okay. Well, yeah. I mean, hopefully you're seeing a pattern emerge. And that's important to notice, that comb filtering follows a predictable pattern. Okay? It's very, very predictable. If you really focused on this pattern, you could probably keep going and filling in the rest of these without having to do the math, right?
It's not the same number for each, like, different problem. Like, it's not ever going to be
It's relative to t.
to T. Okay. That's
So as t changes, then the pattern changes.
right. Okay.
All right. All right. Here's one of your story problems that you don't like. You ready? So 2 loudspeakers. One is 3 feet upstage of the other. Can you imagine that scenario? So you're the audience. There's 2 loudspeakers on the stage. One of them is 3 feet farther upstage. In other words, 3 feet farther away from you. But you're going to play the same sound out of both of them, even though I tell you never to do that, right? And you don't listen to me, but you do it anyway, and you play the same sound out of both of them, even though Jason said that's dumb and you should never do that, unless you really know what you're doing. But you did it.
But
And now it's going to create a comb filter. Well, how bad is that comb filter? Okay, well, what I want to know are the first 4 cancellations. That's the answer I'm looking for, right? Well, okay, so I'm looking at this equation, right? And to solve this equation, I need a value for t. So what is t in this scenario?
3. No. We gotta convert it from feet. Yes. No.
Let's start by going, let's convert it to time first. So we know that distance and time are very closely related in sound. So what is 3 feet in time? So we know that sound travels 1,130 feet per second, right? We know that. Because I told you that. Even though here in Winston-Salem, North Carolina, it's 1,050, but we're pretending we don't know that for now. Okay? 1,130 feet per second. Okay. So how many feet per millisecond is that? Divided by 1,000, right? Divided by 1,000. And that gives you 1.13 feet per millisecond. Okay. So 1.13 feet per millisecond. So here's the short, that 1.13 is a magic number. Okay? When you're converting between distance and time, this 1.13 is the magic number you use. Now, what you might notice is that the distance value is always higher than the time value when you're dealing with sound, hopefully. Unless something really weird is going on. Okay?
What could make that happen? If you could think of a quick example.
If it was really, really hot,
Really? Okay.
then yeah. So if it was really, really hot, then maybe you could get to the point where you would cross that line of it being the other way around. But you're hardly. I've never been in that scenario. I've been the other way. I've been the way where sound goes way slower than you think it will, and when it's really cold, that's weird. We went to for intensive art several years ago. We went up to Boone, North Carolina, and there was this old theater that had been a movie theater or had been converted to a movie theater, and they wanted to convert it back to a live theater, and they had like gutted it, like it was just completely empty. And it was the middle of December, and in Boone in December is pretty cold. And so there was nothing really in this room, but they wanted us to come and do a little class about acoustics analysis and try to tell them, hey, what should they, if they build this thing back up on the inside, what should they do? Where should they put the walls and all that kind of stuff to make the acoustically better for live shows? So we're doing our little measurements, and nothing is making sense. Like, nothing that we're measuring with our software is making any sense at all compared to like what we're looking at. The math isn't working, like the graphs just don't make sense. And we wrestled with that for a good hour or two as we're all sitting there shivering, you know, with our coats on and everything in this empty room with no heat in the middle of December in Boone, North Carolina. And eventually we realized, oh, it's below freezing and sound is going a lot slower than it usually goes. It's very cold out. It's very cold in as well. And the sound is moving a lot slower than it usually moves. And so that's why nothing's making sense. Anyway, so we had to sort of...
have more questions about that.
Yeah. Okay, so back to this though, 1.13 feet per millisecond. So the distance is almost always more than the time. And therefore, if you want to go from distance to time, you are going to divide by 1.13. If you are going from time to distance, you are going to multiply by 1.13. Okay? So when I say 3 feet, we're going to say 3 feet times divided by 1.13. So I'm at distance. Distance is always more than time in sound. And so I want to convert distance to time. So I'm going to divide the distance by 1.13. What is 3 divided by 1.13? Seth says 2.65. Connor says 2.65. Reese says 2. Okay, that must be true. Okay, 2.65 milliseconds, right? So what's that? What is that in seconds? Because I need it in seconds for this math.
0.00265.
2.65 divided by 1,000, right? Is, say it again.
0.00265.
Anybody else get that? Yeah, Connor got that. Seth got that. Great. That's T. Okay. So that's T. All right, I want 4 cancellations here. So we're going to do 0 cancellation, 1 cancellation, 2 cancellation, 3 cancellation. That's 4, right? And there we go. So now we can do 2 times 0 plus 1 divided by 2 times T, which is 0.00265. All right. Well, what is 2.00265? 2 times 0.00265.
0.0053.
Lee got that? Anybody else get that? Okay. Well, 2 times 0 is 0, and so all we're left with is 1. So what is 1 divided by 0.0053? Say that again.
I got 188.
188 point what? 68 hertz. There's your first cancellation. Second cancellation is going to be 2 times 1 plus 1 divided by 2 times 0.00265, which is otherwise known as, well, 2 times 1 is 2, plus 1 is 3, so we'll say 3 divided by 0.0053. What is that?
566.04.
Anybody else get that? Connor got that? Seth got that? Okay, must be right. Next one is 2 times 2 plus 1 divided by 2 times 0.00265. Well, 2 times 2 plus 1 is 5, right? So 5 divided by 0.0053. Now, the pattern you're realizing is ultimately you're just doing odd numbers here. 1, 3, 5, 7, 9, 11. You can keep it, there's shortcuts to this math, right? I'm just doing it the long way.
But you're just multiplying the original solution by the numerator each time.
Yeah. So now what's 5 divided by 0.0053? Say what? 9 what?
943.4.
43.4 hertz. So a shortcut to this math is just figure out t, and then for cancellations, you just do 1 divided by t, 3 divided by t, 5 divided by t. Right? So on and so forth. Well, 2 times t, I guess, in the case of cancellations, but you get the idea. Okay, last one, which is 2 times 3 plus 1 divided by 2 times 0.00265. Well, that's going to be 7 divided by 0.0053, which gives us what?
1,320.75.
132075, is that what you said?
Yep. Connor got that? Anybody else get that? Reese got that? Okay, good. Must be right. Hey, there you go. We did it. Da, 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 da. This isn't too bad, right?
It's not. It's just lengthy.
Well, I'm doing it the long way. But now that you see how it works, you realize there's a lot of shortcuts that you could exploit here if you wanted to. If it's making total sense to you, and you're like, oh, I totally get this, and yeah, there's like 3 shortcuts that could make this way easier, go ahead and do it. If you have not gotten there yet in your brain, where you're like, oh, I totally understand this equation and how it works, and I'm going to, if you haven't gotten there yet, then don't do the shortcuts. Just do it the long way, and then it'll make a heck of a lot more sense to you.
The only thing that I kind of got lost on was the beginning, because I was focusing on one part, and then by the time I looked back up, you had like in the top right corner all of that.
Yeah.
So if you could just really quickly
Okay.
explain. You don't have to go in depth or anything. Just,
So 3 feet, that's the difference in distance.
right.
So I'm asking, how much is that in time? Well, to go from distance to time, I divide by 1.13. So 3 divided by 1.13 gives me 2.65. That's in milliseconds. I need it to be seconds, so I divide it by 1,000 and I get 0.00265.
Oh, okay. Never mind then. I knew what was going on. I just thought it
Yeah.
was weird. Okay.
Okay. Now, here's it gets a little hairy.
I just said it was fine.
If a comb filter has its first reinforcement at 1.5 kilohertz, what would the first cancellation be? Okay. Well, so this is just sort of like another example of you don't always get to decide what information you're told. Okay? In this case, I'm not telling you time. I'm just telling you a frequency that is being manipulated, and you have to get time, right? So ultimately, I'm saying, okay, we've got a first reinforcement at 1.5 kilohertz, and I say, what's the first cancellation going to be in that scenario? Well, to figure out cancellations, you've got to have a value for t. Okay? Now, I'm pretty terrible at algebra, but I know people who are really good at it, and they have told me that basically, if I know a reinforcement frequency, and I want to use that information to solve it for t, to find t, I could invert this equation and get this. That is the reinforcement equation solved for t. Okay? I don't fully understand how we got there, but I trust the people I know who are really good at algebra, and I've done this math and it works. Okay? So you don't need to know how we got there, but that is the reinforcement equation being solved for t. Okay? T equals I plus 1 divided by the frequency that you're caring about. Okay? You had a question?
No, I said I could have explained it through reinforcement.
Yeah.
Yeah, you just
Not important for purposes of our discussion today. If you understand how we got from there to there, awesome. You can do it yourself. You don't have to memorize it. Those of you who don't get how we got there, just memorize it, and then you don't have to worry about it again. Okay?
Oh, that's okay. I thought you just went, nice.
Okay, so we got to find t first. So t is going to equal I, and if the first reinforcement, what would be the value for I for the first reinforcement? 0, right? 0 plus 1 divided by the frequency that we're concerned about, which is 1.5 kilohertz, otherwise known as 1500 hertz.
Could we do it in kilohertz, or is it just easier to?
You could, but you'd have to change a bunch of other stuff too.
Okay, I was wondering if we needed to like
Yeah.
always.
Just remember, kilohertz is an abbreviation, right? It's just here's an interesting thing, and you're going to see this as we go through all this math. Sound people really don't like numbers that have more than 3 digits in them. And we go to extraordinary lengths to avoid having to think about numbers that have more than 3 digits in them. Now, a kilohertz thing is one of the reasons. That's an example of like, okay, I can do kilohertz, and then I can just write 1.5 instead of 1500. And that's a fairly tame example of the lengths that we will go to avoid numbers that have more than 3 digits. But we actually invented an entire unit of measurement that is derived using logarithms so that we could avoid having to express loudness in numbers that are bigger than 3 digits. Which is just like, that illustrates the special kind of like crazy that we are as sound people, is that, it took us longer to do that logarithm than it would have taken us to just write the number in pascals. But But that's just how we are. I once spent 3 months writing a computer program to save me a single walk up a flight of stairs during tech.
How would
Because that made total sense to me. Of course I would spend 3 months writing a computer program to save me one walk up a flight of stairs to push a button.
you could have just created a pulley system to hit the button?
Or I could have just told somebody, go up and push that button.
Yeah, like
Right? I
that's
mean,
what their options. The determination is great with fast.
but this is how sound people are. This is how we are, right? Is we just, we go to extraordinary lengths to make things easy for us. Okay? We will put in crazy amounts of work to make something else easy. It's weird. All right. Nonetheless, here's the math. So 0 plus 1 divided by 1,500. Well, that's just 1 divided by 1,500 equals what?
0.0007.
Did anyone else get that? Connor got that?
Yeah, I did 0.00067.
6, 7?
It's a rounding error.
Well, which one do you guys want to go with?
There's 4 zeros, 4 sixes, and 1 7.
0.000. Let's do 6, 7.
At the end of the day, it's a rounding error.
Just for fun. Why not? 0.00067. All right, well, that's t, right? That is t. Therefore, first cancellation, great, now we can do that. So first cancellation is going to have 0 for I, right?
You finally saw it? Oh no.
So the first cancellation is going to be 2 times 0 plus 1 divided by 2 times 0.00067. All right. Well, 2 times 0 plus 1 is 1, right? What is 2 times 0.00067?
00134.
That's what I got.
But, I mean, technically, it would be 0.00133 if we did the exact number.
Okay. Well, this is close. Close counts in sound, as you'll find. Okay, 1 divided by 0.00134. What is that?
So fucking long.
746.27.
I got 729.
I got 746.26.
So 1 divided by 0.00134. That's the number we're talking about here.
Oh, okay. Yes, I got that.
That's what you got?
Yeah, 746, 27.
There you go. That's the answer.
Yeah, it'd be 27.
So just so you know, because close counts in sound, what was the other answer somebody else got?
0.0007 for time.
Yeah, but what was the frequency that came out of that? Like Jasmine, you had a different
I got
frequency.
729.
729. Oh, that's a big difference. I don't know what you did there.
I did it wrong. I typed it wrong.
So maybe you rounded time a little bit differently, and you might end up with 747. Well, guess what? We cannot hear the difference between those two sounds. We can't. Our ear brain system can't do that. Okay, and so I have done my best to program the Canvas test to account for this. So if I could not hear the difference between your answer and my answer, then yours is right. Okay?
What's the gap then?
It depends. Depends on what the math is. But I try to account for a certain margin of error there to account for that fact of could I hear the difference? And that's just to save me some time grading. And if it still grades you wrong, I will go look at it. And if I look at it and go, oh, could I hear the difference between that? And if the answer is no, then I'll give it to you.
I thought of you just sitting there grading and having like a frequency generator on your computer and being like, I don't know, it's a little far off.
Yeah.
Let me see if I can hear it.
Okay. Everybody okay? Connor, you got a question?
Yeah.
So by that same token, when we first saw it, since we know that the first cancellation is always going to be fraction of first reinforcement,
Yes, if you are spotting the pattern, you would see that yes, 750 hertz would also be a correctish answer.
And I mean, I don't necessarily care. Canvas quiz would say that is close enough, presumably.
Probably. Maybe, I don't know. I don't know what the tolerances I put in there. But yeah, we would also have a very hard time hearing the difference between 746 and 750 hertz. If we played them both at the same time, we'd hear them pulsing. But if we played one and then played the other, you'd be like, that's the same thing. That's a tuning error on your instrument, right? Okay.
So, well, for us to, like, let's say it's like 746, right?
Yeah.
How far apart do the sounds have to be for us to actually hear the difference?
It depends, because our resolution of the differences changes depending on where we are in the frequency spectrum. So, like a 10 hertz change, like the difference between 100 hertz and 110 hertz, we can hear that, but we could not hear the difference between 10,000 hertz and 10,010 hertz. That's the same difference in frequency,
But you just can't.
but we would not hear the difference up at 10K, but we would hear it down at 100. So it's just our hearing system is very bizarre that way. The resolution is not linear. Okay. All right, I got another one. Let's say you're trying to make a comb filter. Like you want to do it just for fun. And you want to make the first cancellation happen at 640 hertz. And you're trying to figure out, well, how far apart would I have to put these two loudspeakers to make that happen? Okay, well, I'm giving you the first cancellation at 640 hertz, right? So in order I need to find out ultimately a distance. And before I can get a distance, I need a time.
Right.
Okay? Well, again, my friends who are good at algebra told me that solving cancellation formula for t looks like this. T equals 2 times I plus 1 divided by 2 times the frequency. Okay? So that's the first thing I want, is I want to get time. And then I can convert time into distance, and I'll have my answer. Yeah? Okay. So here we go. We're talking about a first cancellation. So that's 0, 0C. Okay? So we're going to do 2 times 0 plus 1 divided by 2 times 640 hertz. Did I do that right? I think so. Okay, well, 2 times 0 plus 1 is 1. What is 2 times 640?
1,000.
Yeah. Some people can do that in their head.
Would we not put a 0 on the bottom as well because there's an I beside the F?
Remember, this is just a variable. It's the frequency we care about, right?
Okay.
The frequency, I stands for 0, so the 0 frequency. Okay. Okay, what's 1 divided by 1280? 0.00078?
Yeah.
Yeah, and unlike the previous one, like this one is a terminating number. So I mean, like if we use the full thing, we would get an exact answer.
So, all right. Eric wants to do the whole thing.
I didn't say that. I just-
0.0078125. That's fine. We can do it. We can do it. We're sound people. We don't like numbers that big, but we can deal with it. All right. So that is t. How can I convert that into distance?
Multiply it by 1.13.
Well, okay. We could do this the long way. The long way would be taking this value and converting it to milliseconds first. Okay? And then from there, we can multiply it by 1.13. Or, since this is already in seconds, and the speed of sound is 1,130 feet per second, we could just skip over that back milliseconds conversion and just go straight to multiplying this by 1,130. Right?
Let's do that, yeah.
Does everybody understand how we got there? We don't have to convert it back to milliseconds first. It's already in seconds.
Right.
And so we can, instead of just doing 1.13, we can do 1,130,
Yes.
which is the speed of sound. Great.
That's what I needed for like the 1.13.
So what is that?
Oh my God.
Eric made us do a big number. Let's do a big number. Say that again. Okay. That's in feet.
Even if you had done just the 7, 8, you still end up with rounding. You still end 0.88.
Yeah. So I would accept that answer. That's feet. What would that be in inches, just as a gee whiz? Because maybe inches would be something a bit more meaningful.
Well, we need to multiply that by 12.
Yeah.
10.5 inches.
Say what? Ish. What is it?
More like 10.6.
10.6 inches? Almost 11. Somewhere between 10 and 11 inches. Yeah.
I'm not going to give the full.
No. No. Okay. There you go. We did it.
Why is this doing this? So weird.
So that is right and that is right. It's either 0.88, 28725 feet or 10.6 inches. Either of those are technically right. On Canvas, I'll tell you what I want. I'll tell you if I want inches or feet or whatever.
Going from time to distance was much better.
No, from time to distance. Time is always less than distance. So if you're going from time to distance, you're going to multiply by 1.03. All right, here's the classic. This is the one that will happen to you all the time, okay? So you're doing a musical. Let's do a musical. And most musicals tend to involve at least one love interest, in my experience. Okay? And so you're going to have these two characters that find out somewhere along the way that they are in love. Okay? And that usually happens, they usually kind of start realizing it in Act 1, but in Act 2 they start, actually talking to each other about that. And so sometime in Act 2, they are going to sing a song together about how they've realized that they both love each other. And isn't that swell? Okay? And when they sing that song, there will be a point in that song when the choreographer or the director, whoever is driving that particular bus at that time, is going to tell them, okay, at this point of the song, and it's usually the climax of the song, the most important part of the song, the most exciting part of the song, at that moment, they are going to lock into a very interesting harmony. Okay, that's going to happen. Okay, they're going to suddenly start harmonizing with each other, meaning that one's going to sing one note, the other's going to sing a different note, and those two notes sound really cool together. Okay, because now they're in love and they're vibing, right? Okay, so they're going to harmonize together, and in that moment, that director or that choreographer is going to bring them this close together, so they can stare into each other's eyes lovingly as they harmonize.
Yes.
Happens every musical. Okay, every single time. Well, here's what happens. You have a microphone on each of them, right? And those microphones are omnidirectional. Omnidirectional meaning they pick up equally no matter which direction you point them. Now, there is a reason we do that, because the Purdue Committee tends to have something to say about where we get to put the mic, okay? I always tell them, I don't really care where the little transmitter pack goes, but I really care a lot about where the end of the mic goes. And I try to really get that where I need it. But sometimes the costume designer is going to put a hat on them or something, and sometimes I can win that, but sometimes I can't. And when I can't, I end up putting it in a really bad place. Like over here at the ear is a terrible place to put a mic. It just sounds terrible. And but anyway, that's why we use omnidirectional mics, because that helps us given that we can't always get the mic in the absolute perfect place. The absolute perfect place, by the way, would be right here in front of their mouth. But we never get that. I've only got that once, actually. It was amazing. And it sounded great. But every other project I've ever done, I've never gotten it. I only got it once.
Musical?
It was a musical.
And did you calculate this
No,
well?
I didn't have to, because I got the mic in the absolute perfect spot, and so I got to use cardioid mics. Pointed straight at them. And so when they got right next to each other and singing into each other's face, they were lined up with the nodes. And it was great. It was
Sounds great.
great and glorious.
It's the best day of my life. I'll
Yeah.
never forget it.
I wrote it in the history books.
I've journaled about it later that night. I used my
And lo, there was a day when the microphones were in the perfect spot.
in a few years. You
dream
pull
about
out
it,
the
yeah.
exact date and
Yeah.
time, and you're like, it was wonderful.
So it's an omnidirectional mic, which means it picks up equally in all directions. And that helps it sound not as bad when we end up having to put it in a really weird spot on their head. But that also means it picks up not just that person really well, but everyone around them and everything around them. It picks that all the sounds that happen around this person get picked up by this mic as well. Okay? Including the person that is now 6 inches away from their face. Okay? So it's going to pick up the actor's voice that is wearing the mic, and it's going to pick up the actor who is standing 6 inches away from them. It's going to pick up their voice just as well. Okay? Because 6 inches is not far enough to travel for the sound to have decayed in level any noticeable amount. And so you have a microphone picking up two sounds, right? Well, that's not a big deal, because they're two different sounds, right? It's not a big deal. That mic's picking up that person's voice and another person's voice. Those are different sounds. That's not a big deal. Comb filtering only happens when it's the same sound, right?
You said they were harmonious, right?
But there's also two mics.
Ah, that's right. The other person is wearing a mic, and that mic is also picking up both sounds. Okay? And then what happens with those two mics? Where do those go? They go into your mixing console, right? And what do? You mix them together, because you want both of those sounds to come out of the sound system, right? So suddenly, boom, comb filtering on the wire. You combine two identical sounds, because now, yes, even though each mic has two different sounds in them, but they both have the same two different sounds, and those sounds are different times, right? Because the person's voice that is wearing the mic will hit their mic at a different time that it'll hit the person across from them. That's going to be half a millisecond later. That happens. So that mic hears it a half a millisecond later, and then you sum them together in the mixer, because that's what you do, and then it comes out of the entire sound, comes out of every loudspeaker in the entire sound system like a comb-filtered mess. Okay? And half a millisecond is the kind of comb filtering you can absolutely hear. Yes. So.
If their mics are EQ'd differently, does that fix it at all?
Not really.
Slightly different sounds?
Not really. It might affect it ever so slightly, but not enough to save you.
That's a good question, so.
Not enough to save you, unfortunately.
I don't know. I was just like, I didn't think about
All right, so what kind of problem are we looking at here?
We're finding.
Let's, I don't specify which thing, so let's just focus on the cancellations, okay? So let's just do 3 cancellations. So 0C, 1C, 2C. Okay, well, 6 inches, what would that be in time? 6 inches is 0.5 feet, right? Hopefully you don't need a calculator for that. What is that in milliseconds? We divide by 1.13, right?
See, that's where I keep.
So what is 0.5 divided by 1.13? Say that again. 0.44 milliseconds. Seth is giving me a very confused look. Why are you confused, Seth?
I don't know. I don't think I know.
Okay. 0.44 milliseconds. What is that in seconds? Divided by 1,000. And I get 0.0044. Yeah?
So the first one we do is to convert it from distance
Yeah.
to time.
I got to get t, right? I'm looking for t.
Right, and then the second equation is dividing it by
To go to milliseconds to seconds.
the seconds.
Yep,
Yeah.
because I need it in seconds.
Okay.
Okay?
Actually, I guess I was thinking.
And we
Like,
just need,
I was like,
we
I
just
know,
need it
but
in
I'm
seconds
confused.
because
The
it's
only reason
easier,
I'm
right? We
confused
don't have to convert anything else.
Is why wouldn't we have just divided it by the 1130, and then we would have arrived at that second's answer first?
You could.
Okay. I think that's why I was like, why are we going to?
Yeah. If that makes sense to you, then do that. Yeah, absolutely. That's one of those shortcuts. The only reason I'm doing it the long way is I want to drive home this concept of 1.13 feet per millisecond. That's a magic number that you're going to need to know many times throughout this semester. Okay? So I'm doing it the long way to just drive that home. Okay? But yes, if you are seeing that there's a shortcut, by all means take it.
Good job, Seth.
What was the shortcut?
The shortcut is we could just say divide by 1,130.
Yeah, we could have avoided going to milliseconds and back.
Yeah. All right. So let's find this out. So we're going to do 2 times 0 plus 1 divided by 2 times 0.00044. Okay, well, this is 1 divided by, what is 2 times 0.00044? Yeah. Okay, what is that? 1. 0.3. Anybody else get that?
I mean,
1136.36.
I don't know. I'm doing it on my calculator. I'm just like keeping the answer, so I
Okay.
Yeah.
1130 even. Because I'm keeping the answer. Like if you like just use the answer and divide, like
Oh, I see.
instead of doing it rounding.
Yeah. So there's some rounding going on here. That's fine. That would count. All right. So next one is going to be 2 times 1 plus 1 divided by 2 times 0.00044, which is going to equal 3 divided by 0.00088. That's an 8. What is that? 3 divided by 0.00088.
3,409.09.
3409.09. Anybody else get that? Yeah? Okay. This one is 2 times 2 plus 1 divided by 2 times 0.00044. That's going to be 5 divided by 0.00088. What is that? 5685 point what? 81.81.
0.82, but it doesn't matter.
Okay. All right, so this is kind of really bad news. Because usually our job in this scenario is we are trying to deliver intelligibility. Now, when people, what happens is the reason sound designers were invented is because,
Just popped out of a machine.
yeah. Sound designers were invented because there was a lot, people like to, you'll hear a lot of people say, well, back in the good old days, we didn't have to put mics on everyone because the singers knew how to sing and the theaters were good and orchestrations were better and all this stuff. And I'm like, yeah, and we didn't need mics and sound designers and all this stuff. And like, yeah, I'm not buying it. And the reason I'm not buying it is because if that was true, we would never have invented sound designers. If that world was so perfect, there would never have been a reason to invent a sound designer. Okay? But sound designers were invented in part because there was a long time when people were sitting there going, I can't hear it. And that was going on for hundreds of years. I can't hear it.
That's hilarious. In the Coliseum, people are dying. I can't hear it.
Right? What did they say?
They're dueling. What?
I can't hear it.
Screaming.
Project. Make it louder. I can't hear you. Yes.
Is that supposed to be 1, or is the
Yeah.
crowd just stretched out?
5, 6, 8, 1. 22. Now, so that was going on for a very long time. And eventually, the world decided to invent sound designers to try to fix this finally. And so now we exist and we get to fix it. But part of the way we figured out how to fix it is that we understood that when people say, I can't hear it, they actually meant something different. Because they could hear it. They could hear that person talking and singing. They could hear those instruments. They could hear everything. They just couldn't understand it, right? So when they say I can't hear it, what they meant was I can't understand it. And so one of the first things we did when we were invented and started to figure out how to solve this problem, we said, okay, well, what is it about someone's voice that allows you to understand what they say? And it turns out that that is called intelligibility. And intelligibility is our ability to understand each other. How clear is it? Can we understand it? It's not about how loud it is. It's just how clear is it? And it turns out that the frequencies that contribute most to intelligibility are like 1 kilohertz to 4 kilohertz. That's the range of frequencies that resonates in our ear canal. Those are the frequencies that we're really good at hearing. We're the most sensitive to those frequencies. And we're the most sensitive to those because those are the ones that allow us to understand each other. And so we started focusing on delivering that range of frequencies. Okay, if we do nothing else, we got to get that range of frequencies, those couple of octaves, we got to deliver that better out to the ears. Okay? So that's what we're focusing on when we're in that kind of scenario. And guess what we just did? Well, guess what the director just did? The director just killed that. The director just obliterated that spot of frequencies that is the most important part of it for us, right? So the most important point of the show is when they finally profess their love for one another. And there's the climax of that song, the moment in that song that everyone's supposed to remember is the moment when we obliterated intelligibility. And we didn't do that. We, the sound people, didn't do that. The director did that. Because the director squished them together. I've only successfully explained this to one director in my life. I've only been able to get one director to understand this. What's that? Gerald Friedman.
Of the Friedman Theater?
Yeah.
Wow! Gerald! He's lived up to his name.
And I loved Gerald. Gerald was he was a sound designer at heart. He was a famous director, but boy, that man understood sound design. He did not hear very well because I did a lot of shows with him when he was later in life in his 70s and 80s. He did not hear very well then, and so he trusted me a lot because he was like, well, I don't know, I can't hear it, but is it okay, Jason? Yeah, it's fine. And
He's got me.
And but anyway, I finally convinced him because I was like, Jerry, stop it. Will you stop putting them close together? I was like, why is that so bad? And I was like, let me show you. And so we did it. We went back and we just let them sing, and I let them walk close together. And I'm like, okay, can you hear that?
No.
And he's like, I don't know. Let me mute one of the mics. Oh, well, that sounds fine. Let me turn on the other one. Oh, that sounds bad. Okay, that's what I'm talking about. Will you stop doing this? He's like, oh yeah, okay, I can stop.
Gerald's fine.
Sure, why not? But that's the only time. Otherwise, the director's going to do that. And so they're just going to obliterate the most important spectrum of frequencies at the most important time in the show. And then it's going to sound crappy, and everyone's going to look at you and going, I can't understand what they're saying. It ruined that harmony, the music director's going to go, the beautiful harmony. It got all messed up. And I'm like, yeah, because they're like this close together. So what do? Well, you got to you got to make that comb filtering less, right? There's a few ways of doing that. One way to do that is you can manipulate the amplitude a little bit, right? The comb filtering is the worst when the two sounds are the same amplitude. So if you can decorrelate the amplitude a little bit, that'll help. So yeah, Connor was doing this with his fingers, which is like, yeah, you can like duck one of those two faders a little bit. That'll help. There's another thing. What could the director do if you could explain this to the director and convince them to fix it for it? Move them farther apart, right? Move them farther apart. Well, okay, what happens when they move farther apart from each other? Well, T changes, right? That value of T changes. And when T changes, what happens to the comb filtering? It changes too. It actually gets worse, right? It shifts that first cancellation to a lower frequency. And then suddenly all those cancellations get really close together in that 1 to 4 kilohertz range, where it exploits the critical bandwidth. So, and also it gets quieter, right? So when they get farther away from each other, they're not picking up with each other's mics as loud. So yes, ducking one of the faders accomplishes half of that, right? The other thing is you could add a little bit of delay to one of the mics. So if you could add about 5 milliseconds-ish delay to one of those mics and duck it in level a little bit, then you have effectively accomplished the same thing as them walking farther apart.
What would happen if, say we're on a console and we're using like scenes and we're tapping through, and
Yeah.
in the middle of the song you keep all the settings the same, except for when they get really close, you switch to the next scene.
Yeah.
That specifically addresses the EQ of both of them, and you add like a bump in the frequency between 1 and 4 kilohertz.
No, because remember, you can't EQ a cancellation.
Okay,
It's gone.
gotcha.
The EQ can't make it come back,
Gotcha.
okay? But it also moves, right? Because
Right.
they're not going to stand perfectly still in that moment. They're going to do this a little bit. And that means that cancellation is going to move. And so there's no EQ filter that'll like not lock into that thing and keep it. So, but what you can do is you can add into the scope of that snapshot on the board, you can add a little bit of extra delay for one of those mics and put that into that scene. And an extra 5 milliseconds, if someone just like, if it's just me, if 5 milliseconds is I'm just 5 feet farther away. So I'm here, I'm talking, or I'm here, I'm talking. You don't hear the difference between that, right? With it's just me. So you could actually have that extra 5 milliseconds on there for the whole scene if you want, right? And it only becomes important in that moment when they get close together. And it's this like extra little yardstick you stick between them. Just like you shall not ever be closer than 5 feet, okay?
Does it need to happen on the same mic, or can it be either or?
Either or,
Okay.
doesn't matter. So anyway, there's a little trick, okay? You want to fix the comb filtering? Hopefully you can get the director to fix it, but if the director can't fix it, then duck one of the mics a little bit, add 5 milliseconds to delay to one of the mics, and you will be basically there, okay? All right, you should be able to, there's one more of these. We don't have time to do it, but it's basically the same thing. All right, there's two things I want to just point out here before we end. I don't think this is in the quiz, but when a sound encounters an obstacle, an object that is in the way, the path that it is propagating through the air, it has to decide what it's going to do about that. And it has to decide, hey, can I get around that? And the answer is always yes, I can get around that eventually, unless it's infinite. Unless that surface is infinitely large, that sound will eventually find a way around it. But if that obstacle is small relative to the wavelength of the sound that is hitting it, then it will go around that object like it's not there. It's acoustically transparent. Okay, that object is insignificant because it is smaller than the wavelength of the sound that is hitting it. Okay, but if the object is larger than the wavelength of the sound that is hitting it, then it's going to have a harder time getting around that. It'll find a way eventually, but it will leave a little shadow by the time it finds its way around it. You're going to have this little area here where it's going to be a little quieter. The point here is sound sees obstacles, not gaps. Okay, and this is very important for when you have to deal with the pretty committee, because the pretty committee for some reason hates seeing speakers, right? They're quite happy to look at like 10,000 lighting instruments, But you put one speaker in the picture, and it's the end of the world, right? And I don't understand this, but it's like big deal. So they're gonna want you to hide that thing, and they are gonna have this brilliant idea. They're gonna say, I know, let's put it behind this wall, and we'll poke some holes in the wall, and then the sound can come out. Okay? Well, that's fine, but you are an intelligent sound person, and you know that sound sees obstacles, not holes. And so you're going to say, well, that's fine as long as the gap between the holes is smaller than the wavelength of the highest frequency you want to have get through that. So if you want to make sure that 4 kilohertz and below gets through that, you would calculate the wavelength of 4 kilohertz. And you would say, whatever that is, you say the holes need to be no more than that much apart.
That's so cool.
Okay?
That's so cool.
Next thing is,
It's just scenic.
this is the last one, is the effects of wind and temperature on sound. So I told you that sound moves faster in warm air than cold air. Well, what if you do a show outside? Well, let's say you're doing outdoor theater. You tech the show during the day. Sun's beating down on the ground all day, and then you're going to do the show at night. Sun goes down. Guess what? The air cools off, but the ground is still warm. You have a temperature gradient. So now that sound is trying to hit the audience, and it's pushing against a difference in temperature. It moves faster at the bottom than it does on the top. That has the effect of the sound curving upwards, and suddenly your show is all wonky. Okay? The opposite is true in the morning. So when the air is warm and the ground is cold, it moves faster up at top, and therefore kind of like trips over itself. Goes boom, 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 and like stumbles across the field. This happens inside too, inside of really large theaters. This doesn't happen so much in small theaters. Ever done a show where you show up to opening night, suddenly there's people there and everything's a lot quieter? Okay, that is partly, so everyone says, oh, well, the people are just soaking up the sound. Well, that's a little bit of it, but really empty seats soak up a lot of sound too. There's like padding in there. So yes, the people soak up some sound, but that doesn't entirely explain the problem. What does explain the problem is you just tech the show for a week in an largely empty room. There's like 10, 20 people in there, and it has an air conditioning system designed to cool 3,000 people. Okay? So that room's going to be cold. That's why tech is always cold. That's why everyone's always wearing blankets in tech, because you're sitting in this empty room with this air conditioner that's trying to cool 3,000 people, and there's 10 people in the room. Okay? So those 10 people are absorbing a lot of that cold, right? Well, suddenly you fill the theater full of 3,000 enormous hot water bottles, which is what human bodies are. Okay? And suddenly that ground where those seats are gets really, really hot very, very quickly. And it takes a while for the temperature to kind of equalize. And so for the first couple of scenes of the show, you've got this massive temperature gradient, and all the sound is going up to the ceiling. Okay? And you're going to freak out, and you're going to start changing everything. And then you realize a little bit later that it's like, well, now it's weird again. And you start changing everything back. Has that ever happened? Yeah. Well, this is why, because the temperature evened out, and it's fine now. So, because eventually the air conditioning cooled off the hot people. There you go. Okay? There you go. Same thing for wind. Wind puts the sound, it goes up. Wind goes with the sound, it goes down. There you go. That's it. We're done. Sorry.